Let's look at the practice test for test 2. Number 1 says calculate the standard score and gives us the x, mu, and sigma we need. So our formula here for z, our standard score, x bar minus mu for x minus mu divided by sigma. Okay, so we'll have 26.8 minus 33.7. Divide that by 30.4. It says round to 2 decimal places. So let's see what we get here. 26.8 minus 33.7 equals negative 6.9 divided by 30.4 gives us negative 0.2, and then the next 226 is what I have, so it'll be 0.23. We'll round up. Okay. Just using the standard score formula. Again, I will give you a formula sheet and tables on this test, so you don't have to worry about remembering those. Okay, number 2 says find the area under the normal curve to the left of 1.33. So we'll go to our tables here. So we want area to the left, so we can go negative infinity to z, I believe. What was our z value? 1.33. So yeah, so I'll look up 1.33. So that'll be this row. Nope. This row 1.3 and then 3, so 0.9082 should be our answer there. We got 1.33. Okay, so 0.9082. Okay. Number 3, it's a little bit different this time because it says find the area to the right of z. Okay, so the way I'm going to do this one, you can do it differently, but I'm going to look up negative 1.00. Since it's to the right, I'm going to look up the opposite of what it gives me. So I'm going to look up negative 1 here. Maybe. There we go. So go to the negative side of the table. Look up negative 1.00. Give me an area of 0.1587. And so since it said area to the right, I looked up the opposite. Number 4 says find the area between these two z values. We got negative 2.74 and positive 0.48. So when we want the area between the two z values, we just look them both up, just like they're written, and we subtract. Okay. So I'm going to look up negative 2.74 first, since I'm already on the negative table. So negative 2.74 will be 0.0031. And I'm just going to make note of that. And then I want positive 0.48. So I've got to go over to the positive side. Positive 0.4. Then I'm going to scroll over a little bit. 8.48. 0.6844. Since I want the area between, I want to subtract. We put the bigger one first because our answer can't be negative. Okay, so what do we get there? 0.6844 minus 0.0031. Again, 0.6813. The area between those two z values. So look them both up and subtract. Okay, number 5 says trucks in a delivery fleet travel a mean of 110 miles per day with a standard deviation of 17 miles per day. The mileage per day is distributed normally. Okay, when we see this, that means we're going to use the z table somewhere in the problem. Find the probability that a truck drives between 135 and 144 miles in a day. Okay, so we want the probability of being between these two. So these are our two x's. Gives us a mean, mu, of 110. And it says our standard deviation, sigma, is 17 miles per day. So we got to use our z formula twice. Okay. For the first one, we'll use 135 as our x. And so 135 minus 110 divided by 17, and we'll round to 2 decimal places. Okay, 135 minus 110 equals 25 divided by 17. When we round, we get 1.47. And we'll do the same thing with 144. So what we're doing is we're going to calculate these z's and then find the area between the z's because we have tables for those. Okay, so 144 minus 110 is 34 divided by 17. Comes out to be 2. Since we're using 2 decimal places, we'll call it 2.00. Okay. Now I need to look both of these up in the table. Okay. We look them up just like they're written, so let's see, we'll go to 1.47 first. We on the right table? Let's make sure. Yeah, we are. So 1.47 will be 0.9292. Then we'll look up 2.00. If I go back to our tables here, 2.00, I know it's a little crooked here, but it'll be 0.9772. So then we're going to subtract because it says area between. Put the bigger one first, so 0.9772 minus 0.9292. What do we get there? 0.9772 minus 0.9292. We get 0.048. And if you want to make it 4 decimal places, you could add a 0. But dropped my pen. Okay. All right, so number 6. Get our circle out of the way there. Number 6. The life of light bulbs is distributed normally. That tells us we're going to use the Z table again. Standard deviation of the lifetime is 20 hours, that's sigma. And the mean lifetime is 560 hours, that's mu. Find the probability for a bulb lasting at most 573 hours, that's our x. Okay. So we're going to use our Z formula again. Our x is 573 minus the mean of 560 divided by our standard deviation of 20. Around to 2 decimal places here, so 573 minus 560 gives us 13, divided by 20 gives us a Z of exactly 0.65. Okay. Now, on the last one it said in between, so that was pretty easy. On this one it says what's the probability that we have at most 573? So as far as a mathematical symbol, what does at most mean? That means less than or equal to that, right? 573 is the most we can have, so we want less than or equal, and since that's pointing to the left, we want the area to the left of 0.65. So that means all we do is we look up 0.65 in our table. Okay. We're on the positive side, 0.65. I get 0.7422. That is our probability. Okay. 7 says what value of Z divides the standard normal distribution so that half the area is on one side, half the area is on the other. That's just asking what Z value is in the middle. Okay. The Z value that's in the middle is 0. And you got negatives over here, you got positives over here. The one that's in the middle is a Z value of 0. That is the mean of our standard normal distribution, is 0. And if you're being real picky on this one, it says use 2 decimal places, so we would say 0.00, but not a big deal. Okay. Number 8, it's a little different. This one says find the value of Z, and it gives us the area. It says this area lies to the left. Okay. So what we're looking for here is we're saying we've got some Z value, and we've got an area of 0.0700 to the left of that Z value. What's our Z value? So that means we're going to go to our tables and look inside the tables. This is from section 6.4. We're going to look inside the tables to try to find an area as close as we can to 0.0700. Okay, so these areas are too big. Right? They start with point some other number. We want 0.0 something, so I'm going to go over to the negative side. Now we're looking in here at these numbers. We want 0.0, and then we want our next digit to be 7. Okay, so here are our two close candidates. This one is 6 10,000ths away. This one is 8 10,000ths away. So we go with the closest one. So our z value here would be negative 1.48. That's as close as we can get to 0.0700. So our z value here is negative 1.48. Okay. Closest we can get. Number 9, same type of problem. I want to find the value of z such that we have this area. This time is to the right of z. So if we make a little sketch, is we got a z over here, and we want this area of 0.0400 to be to its right. Okay. And remember, this keyword here, right, tells us we can do the opposite. So what I can do instead, since it says we want this area to the right, is I can just, instead of having to get too fancy, I can just look for 0.0400 in the table. But whatever z I find, I'm going to take the opposite, okay? Because this thing's symmetric, so we can do it that way. So I'm going to look inside the table for 0.0400. First digit's a 0 after the decimal, and then we want a 4. So let's see. And so here are two that are close, 0.0392 and 0.0401. This one's very close, it's the closest. So this corresponds to a z of negative 1.75, but we want the area to be to the right. So instead of negative 1.75, our answer is going to be positive 1.75. I want the positive one. Okay. Number 10, the supposed SAT writing scores are normally distributed with a mean of 490. Okay, we might as well mark that down. That's mu. And a standard deviation of 112. That's sigma. The university plans to offer tutoring jobs to students whose scores are in the top 6%. What's the minimum score to require for the job offer? So we need to figure out the z value that is in the top 6%, and then we'll change it back to a SAT score. Okay? So here's our picture of what's going on. We want to figure out what z value is in the top 6%. So that means we have an area of 6% or 0.06 to its right. Okay? So again, since we want the area to the right, I'm going to use the opposite trick. I'm going to look for 0.06 in the table. Okay. So here are two that are close. I've got negative 1.56 and negative 1.55. On this one, it's exactly between these two, so we would add them together and divide by 2. We'd do 1.56 plus 1.55 and divide by 2. And if we do that, we'll get 1.555. And remember, I'm not using the negative because I'm taking the opposite. So my z is 1.555. To change that to an SAT score, we have this formula. It says if we want an x, an SAT score, is z times sigma plus mu. So here that's going to be 1.555 times 112 plus 490. Let's see what we get there. It says we can round to the nearest whole number. So 1.555 times 112 plus 490. I got 664.16, so when we round to the nearest whole number, our minimum SAT score is 664. Okay. Number 11 is the average number of classes per semester for a sample of 55 students at the local college is 4.2 classes. What's the best point estimate for the average number of classes per semester for all students? Well, that's gonna, if we're using a point estimate here for an average or for means, then we want the sample mean. And it says for a sample of 55 students, the mean is 4.2. So our point estimate here is 4.2. Sample mean. Remember, the point estimate is our single number estimate we use to start a confidence interval. So it's going to be the sample mean here. Number 12 says the mean amount of money spent on a meal for a sample of 358 students is $6.10. This is the mean of our sample, our sample size. If the margin of error for a population mean with 99% confidence interval is 150, okay, and this is important, this is our margin of error. It gives it to us on this one. Construct the 99% confidence interval. So we already know X bar, and we are already given E, our margin of error. So to make our confidence interval, we just have to add one. I did those backwards. We have to add one time and subtract one time. Okay. So we'll do $6.10 minus 150. That will give us the lower endpoint. So what do we get there? Get $4.60 as our lower estimate, and then $6.10 plus 150 gives us $7.60 for our upper estimate. And if you want to write it like the interval, you can, or you can just do the two endpoints. Either one's okay. Either way is fine. Hawks will get you to put it in like this, so you get the two answer boxes, but you can write it as an interval also. Either way is fine. Okay, number 13 says find the value of t. So we got to use our t-table such that 0.025 of the area under the curve is to the right of t. Assume degrees of freedom equals 6. Okay, so we're looking for our t value here. So we've got an area of 0.025 to the right of t. That means it's in one tail. Okay. And it's to the right, so our t value is going to be positive. So if we go to our t-table, again, I'll give this table to you. And so we're going to look it up by area in one tail. Well, 0.025 in one tail. And it said, what did it say? It said 6 degrees of freedom. And so 6 degrees of freedom gives us our t value of 2.447. If it said the area was to the left, then it would be negative 2.447 because the values on the left are negative. This one's positive. It said the area to the right. So our critical value of t, 2.447. Number 14 says a random sample of 28 fields of rye has a mean yield of 36.5 bushels per acre, a standard deviation of 2.51 bushels per acre. So our sample size, mean, and our standard deviation. But it says assume the population is approximately normal and sigma is unknown. So this is not sigma, this is S. Okay, so we're in a sigma unknown situation. And then it tells us to find the critical t value we should use. Okay, so here's our formula for margin of error. We got this t sub alpha over 2 times s over the square root of n. And this step's asking us this time for the critical t value. It could ask us for the whole margin of error, but this one's just asking us for the critical t. So we need to figure out the degrees of freedom. We need to figure out the area in the tails. Okay, so the degrees of freedom, that's our sample size minus 1. So 28 minus 1, we're going to have 27 degrees of freedom. The area in the tails, we look at the confidence and do 1 minus that. So 1 minus 98% or 1 minus 0.98 tells us we've got 0.02 in 2 tails. If you divide it by 2, it gives you the area in 1 tail, but we don't care. We can look it up by the area in 2 tails. So 27 degrees of freedom, 0.02 in 2 tails. And let's see what we get. So we'll go to area in 2 tails. 0.02 and 2 tails. That's the first column. 27 degrees of freedom gives us a critical T of 1.314. 0.2 and 2 tails, 27 degrees of freedom, 1.314. So I wrote all over this one, but 1.314 is our critical T. That's this number. Step 2 says make the confidence interval. So we've got to finish our margin of error formula. So we know the critical T is 1.314 times our sample standard deviation, 2.51, divided by the square root of our sample size, which was 28. And on these, remember, you want to leave several decimal places so you don't accidentally round too much. So 1.314 times 2.51 divided by the square root of 28. I'm going to leave 6 decimal places here, so I got 0.623 290 how that would round to 6 places. And then now we take our mean, our starting point, and add and subtract this number. So we do 36.5 minus our margin of error, and then 36.5 plus our margin of error. And it says we can round our final answer to 1 decimal place. Okay, so let's see what we get. 36.5 minus 0.623290 is this 35.87, so that will round up to 35.9. And 36.5 plus 0.623290 gives us 37.12, so that stops at 37.1. Those are our 2 endpoints, and you can write it as the interval if you want to. Okay. Number 15 says FBI wants to determine the effectiveness of their 10 most wanted list. To do so, they need to find out the fraction of people. Okay, so that tells you this is a proportion who appear on the list that are actually caught. Suppose a sample of 510 suspected criminals is drawn, so that's our sample size N. Of these people, 178 were captured. Using the data, construct the 85% confidence interval for the population proportion of people who are captured after appearing on the 10 most wanted list. So first, we need our point estimate, the sample proportion, p hat. The way we get that is we do x over n, where x is the number of data values that have the characteristic we're counting. We want the ones who were captured, so we had 178 of those. So 178 goes on the top. N is our sample size, 510. So 510 goes on the bottom. Okay. And if we take our proportion here, 178 divided by 510, and if we round that to 3 decimal places, we get 0.349. So that is our sample proportion. The other thing we need, that's our point estimate. The other thing we need is our margin of error. Okay, so our margin of error is going to be z sub alpha over 2 times the square root of p hat times 1 minus p hat divided by n. Okay, let me look over that and make sure that looks right.